look at example 8. We want to write a differential formula that estimates the change in the volume of a cube when the edge lengths change from x naught to x naught plus this very small amount. Okay. This might seem kind of like you're like sitting there going, now what is this talking about? But it's just we're recognizing variables and everything. It's just being able to create a new equation. Okay. If I normally took the derivative of v, it would be dv dx, because we're taking the derivative of the volume with respect to x. And on the right side, it would be 3x squared. Okay, so if I want to use the whole terminology of x and then changing it by a very, very small amount, all that means doing here is first of all solving it for dv, because it's going to be dv equals 3x squared dx, but instead of x, I'm going to use my x naught. So it's just dv equals 3x naught squared dx. And that's all that they're looking for when you write this equation. Okay? So again, all you have to do is just take the derivative of the dependent variable with respect to the independent variable and just use your x naught terms and then just solve it for dv, or if it was like dy, or if it was ds, just change it for that. So let's go to example number 9. We want to write a differential formula that estimates the change in the lateral surface area of a right circular cone when the radius changes from r naught to r naught plus dr, so just ever so slightly, and the height does not change. Okay, so that means that height is a constant. When it says it's not changing, like we can think of it as like the number 2. Okay, so think of it as just a number sitting in there. Okay, so obviously r is our variable, so we're going to be taking the derivative of the surface area with respect to r, the radius. Okay, and so in here it looks like I have basically a product of two things. As y'all all know, I like to rewrite I don't like to see the square root. I like to write it as r squared plus h squared to the 1/2 power. Okay, to me that seems a little easier, but we got a product rule. So I got a variable here and a variable inside here. So it's going to be the first times the derivative of the second. So 1/2 times r squared plus h squared to the negative 1/2, and then times the derivative inside. And the derivative inside is just going to be 2r, because remember h squared is just like a constant, it would be just a number. Okay. So it's the first times the derivative of the second plus the second times the derivative of the first, which is just pi. Okay, let's keep going with this. So ds dr is going to equal, let's see, 2 and the 1/2 are going to cancel. So I'll get pi r squared times r squared plus h squared to the negative 1/2. All that for the first part. And then over here, looks like plus pi times r squared plus h squared to the 1/2. Okay, so the difference here, when all they want us to do is to write a differential formula, what that means is obviously, first of all, we want to solve this for ds, and then instead of having r's, we want r naughts. So pi r naught squared times r naught squared plus h squared to the negative 1/2 plus pi times r naught squared plus h squared to the 1/2, and all of that dr. And it's as simple as that. Example 10. The diameter of a tree was 10 inches. During the next year, the circumference increased 2 inches. About how much did the tree's diameter increase? The tree's cross-section area. Okay, so reading through example 10, you notice that the diameter of a tree was 10 inches, and the next year their circumference is what's increased by 2 inches. So diameter was 10, and we had a circumference increase of 2 inches. About how much did the tree's diameter increase and then the tree's cross-section increase? So again, just looking back at that problem, just reading through it one more time, but really understanding what it was saying. Okay, so let's start this problem out. We know that circumference for a circle is pi times d. But since the problem asks us is how much did the tree's diameter change, or how much did it increase, that we don't really want to solve this for c, we want to have it solved for d. So instead, we'd rather look at something like d equals c over pi. Okay, and so then when we go start taking the derivative, I guess I'll say the derivative of the diameter with respect to the circumference is going to be 1 over pi, or the derivative of the diameter, the change in the diameter, is 1 over pi dc. Okay, so kind of taking some information that was given to us, the way we can look at it is the derivative of the diameter, or the change in the diameter, is 1 over pi times the change in circumference. Well, the change in the circumference was by 2 inches. So in all, the change in the diameter was 2 over pi. Okay, so that's part of our answer. Let's go on and find another part of our answer. Okay, next thing I want to do is the tree's cross-section area. How much did that change? Okay, well, the area of a circle, of a cross-section specifically, so it's pi r squared. So taking the derivative, you get dA with respect to the radius, dA dr, is going to be 2 pi r, and then moving this around, you get dA equals 2 pi r dr. Okay, so let's fill in with what we know. So the change in the area is going to be 2 pi times the radius. Well, if the diameter was 10, then the radius is 5, and the derivative of the radius, well, because you know radius is half of the diameter, so the diameter is 10, so half that was 5. Well, the change in the diameter was 2 over pi, so we want that to be a half of the change there, so a half of 2 over pi. Okay. So then dA is 2 times 5 is 10 times a half, or a half, if you want to consider that, cancels that, so it's going to be, and the pi cancels there, so it's just going to be 10. And if we go in here and put inches or units in there, so the change in the surface area, or the cross-section area, will be 10 inches squared. Box that up. And then the change in the diameter, I guess I should have put inches right there. Alright, let's go to the next problem. The edge x of a cube is measured with an error of at most 5.5%. What is the maximum corresponding percentage error in computing the cube's surface area? And then the volume. Okay, so going back, and let's just read this problem again. So the x is representing the edge, and the error is at most 0.5%. We want the maximum corresponding percentage error in computing the cube's surface area, and then volume. Okay, so let's get this, I guess let's look first at the surface area. Okay, well, if the side of a cube is x, then the surface area, I'll call it S. The surface area is then, since there are, you know, each side of the cube would be x times x, so x squared, and the cube has 6 sides, so it would be 6x squared. Okay, and then what we're going to do is then take the derivative of that. So ds with respect to the side, so ds dx, is going to be 12x, or that ds is 12x dx. Okay, so ds is going to equal, we have 12, and then what we need to do is figure out what x, or in our case, what x naught, and then what the change in x is. And that's where this whole error is going to be, the error of at most 5%. When it says an error of at most 5%, what that means, or 0.5%, what that means is that basically if you have an x value of 1, then the change is going to be 0.005. Or if you wanted to think about it, if x equaled 100, then the change would then be just 5. But we're going to go by just a unit of 1. Okay, so it'd be 12 times 1 times 0.005. So in other words, the change in the surface area is 0.06. Okay. Now to fully answer the question as far as finding the maximum corresponding percentage error, we use that formula where it's the derivative of your function over the function evaluated at a point times 100. Okay, so how this relates to us is the derivative of our function, which is 12x dx, divided by the function evaluated at a, so we're going to say 6 times x squared real quick, and then we're going to plug in our value. Okay, so plugging in our 1 for our x and 0.005 for our dx. We already know the top value. The top value is going to be 0.06. And down here in the bottom will be 6 times 1 squared. So 0.06 divided by 6, and then multiply that times 100 will give us a 1% maximum corresponding error. Okay? So let's kind of do this exact same process, but now let's go to volume. Okay, so the change in volume. First of all, we need to write ourselves a formula. So the volume of a cube is just length times width times height, so x times x times x is x cubed. So then we start taking the derivative. So the derivative of the volume with respect to x, or the change in the volume with respect to x, it's going to be 3x squared, or dv is going to be 3x squared dx. And if we take that and evaluate it at our initial x naught value, so the change in the volume is going to be 3 times 1 squared times 0.005. Okay? Or in other words, that dv is going to be, by the time we multiply all that out, is 0.015. Right, and then going back to our formula to actually find the maximum corresponding percentage error, we go to take the derivative of our function, which we just found out to be 0.015, divided by the main function evaluated at a, which is 1 cubed, and then we're going to do all of that times 100. So 0.015 times divided by 1, and then times 100 is 1.5%. And there's the answer for the second part.